Hello friends, I welcome you again in the 12th part of this ongoing D block element series. So now we are discussing about the characteristic property, and the first characteristic property is variable oxidation states. Variable oxidation state. Okay, so before I start this topic, let's see, there is a chemistry joke for you. A hug without you is just toxic. A hug without you is just toxic. Do you know why? Okay, let me make you understand. HUG, hug. If we cancel out this U from here, then it becomes HG, and HG, you know, very toxic, in fact carcinogenic. So that's why the statement, hey, hug without you is just toxic. Okay, so we were discussing about the variable oxidation states. Now in this heading, the first thing is that the D block elements, they exhibit, D block elements exhibit variable oxidation states or valencies variable oxidation states or valencies variable oxidation states or valencies due to involvement of NS as well as N-1 D subcells. Now NS subcell will be from the ultimate cell, that is the outermost cell, and N-1 D subcell will be from the penultimate, that is second last cell or orbit. So they exhibit variable valency due to the involvement of both NS and N-1 D subcell electrons, and this is why due to less energy difference between these. So there is very less energy difference, so both they are participate in the oxidation process. That's why the transition elements show variable oxidation state. Now the oxidation states of transition elements, few examples we'll see there. Now here we'll see some example of the variable oxidation states. Here it is a table which contains element from scandium to zinc, their electron configuration. This is the outermost electron configuration, that is D and S subcell, and then here are the oxygen set. Now you see in case of scandium 3 electrons are there, so the oxygen set is +3. In case of titanium it is 3d to 4s2, then 2 plus 2, so oxygen set is 2 is there, 3 is also there, and plus 4 is also there, so 2 to 4. Now there is large variety of oxygen sets is there. Similarly you see more and more, and the most number of oxygen set, highest number of oxygen set you will find in the middle in case of chromium and in case of manganese, where you see there is a large number of d subset electron, 5 d electrons in each, 5, and then one of the S here. In case of chromium 6 total electron, in case of manganese 7 total electrons. So manganese is having highest oxygen set up to +7 and chromium is up to +6. So as you see in the middle, now see this kind of trend is there in the oxygen set. Very few at the top, very few at the top, and large at the middle. So if you see again the graph, very few, 1 or 2 at the top, and again 1 or 2 at the bottom, and in the middle, because here they are highest. As we see, the number of unpaired electron in D subcell reaches the maximum, the oxygen set also reaches the maximum. So this is the chart by which you can just see and observe the variation in the oxygen sets, and even calculate the oxygen sets of anyone. Okay. Furthermore, in some cases +2, in some cases +3, in some cases +7, the different variety of oxygen sets, they are stable. It is due to the number of electron in D subcell. Suppose somewhere there is D5 exactly half filled, there is D10 completely filled. So these are some criteria which are going to decide that for which element which oxygen set is going to be stable. Now if you see the highest oxygen state, highest oxidation state of transition element can be calculated by n+2 number, where n is equal to number of unpaired electron in D subcell. How many unpaired electrons are there in the D subcell? If you see in the middle 5, 5, 5. So as the number of unpaired electron in D subcell, unpaired electrons in 3D, and these are the electrons of 4s. So by this number you can have the maximum number of or highest oxygen set. But this is not applicable in case of what? Chromium and copper. Can I tell you why? Because in chromium it is not S2. Chromium is having 3D5 4s1, and then copper is also having 3D10 4s1. So there the rule will be n+1 in case of copper and chromium, and in other cases it is n+2, by which you can calculate the highest oxygen set. Okay. So